I am not one of the authors of this paper. Unfortunately, they could not make it today. But I'm going to use the pronouns we throughout. I'm not trying to take credit for the work. It's a bit easier. Okay, so what is this paper about? It's about the problem of detecting the boundaries between human and AI-generated text. So for example, here we have a recipe that starts as written by a human, and then it gets continued by an AI. And the problem setting here is just to discover where does the AI-generated text begin. So there are 5 contributions of this work. Firstly, we adapt perplexity-based and intrinsic dimension-based detectors to this task. Secondly, we provide an analysis of how perplexity scores react to the transition in the text. Thirdly, we show that scores from small language models trained on data generated by larger language models can provide strong features for boundary detection. And fourthly, we show that the robustness of boundary detectors to domain shift depends on the particular properties of the text domains and also the generating models. And fifthly, we introduce this real or fake text ChatGPT dataset, which we open source to the community. So we study 2 datasets in this work, and the first one is from prior work called RoFT, which stands for real or fake text, and this was introduced by Dougal et al. In their paper. So each sample in this dataset contains 10 sentences, and it starts always with human text, and at some point it gets completed by a machine, except in certain cases, about 10% of the data is purely human. So there are 4 domains in the dataset: New York Times news articles, short stories, presidential speeches, and recipes. And the models used to generate are a range of different small models. Notice that these are pretty small models, so significantly less capable than the current frontier. And the structure of the dataset, as I've already said, is this prompts that begin human written and they get continued by the model. And secondly, we study another dataset, which is the one that we create and introduce in this work, which we call RoFT ChatGPT. And this is essentially the exact same thing, but we use ChatGPT to generate new completions for all of the datasets, as this is a much more capable model than the one that was used in the prior work. And similarly, we have the same 4 domains of data set, and this time it's just a single model. Okay, so how do we actually do this task? So we try quite a range of different methods. Firstly, we fine-tune transformer models to output the class directly. So we use a RoBERTa model fine-tuned to output the label of the first sentence, which is machine-generated in a special classification token. Secondly, we use detectors that take the perplexity as input. So we use various small models to generate perplexity scores for each token, and then we use this as input to simple classifier models. Thirdly, we have detectors based on intrinsic dimensionality, and these are similarly simple classifiers that use the intrinsic dimensionality of the embeddings of generated by a transformer model. So topological data analysis is the key word here. Fourthly, we tried just asking ChatGPT and GPT-4 to complete the task, 0 shot. We just prompt them to say, when does this text switch from being human written to machine generated, and see how they do. And lastly, we have a few simple baseline methods. So the first one is a length-based detector. It just takes as input the lengths of the sentences and tries to classify when the machine generation begins. Secondly, we just have the modal class, so whichever label is most common where the label again is just the number of the first sentence that was written by a machine. And lastly, there's a human baseline, which is provided by the previous work that introduced the RoFT dataset. Although note that the human baseline was on a slightly harder task because they were shown the sentences one by one and then asked in real time to decide when was the first one that was machine written, whereas with our models, we're just feeding them the entire text at once. Okay, so let's look at the results on the original RoFT dataset. And the first thing to notice is that, yes, basically this task is possible. In particular, the RoBERTa plus SEP model can actually do a decent job. And so what is RoBERTa plus SEP? Well, SEP is the separated tokens that we insert between each sentence, and this just slightly improves the model performance because sometimes there are periods elsewhere in the text that may throw the model. But essentially, this is the fine-tuned transformer, and it outputs the label of the correct class directly. In orange, we have the perplexity-based classifiers, and you can see we've split it out by different models that are used to generate the perplexities. And these generally don't perform so well. And similarly, the topological data analysis doesn't perform very well. These are the bars in blue, and they are TS, which stands for time series, because we use a sliding window over the tokens in order to detect at which point the intrinsic dimensionality changes. ChatGPT and GPT-4, they really just can't do this task, and they actually do much worse than even just the modal prediction. And S-RoBERTa is similarly a transformer trained to output the label directly. This is from previous work. Now let's look at the results on the RoFT ChatGPT dataset, which, remember, is the same thing, but with the completions generated by ChatGPT. And the first thing that stands out is the orange bars are much higher. The perplexity-based classifiers are doing significantly better. Now, this is kind of surprising because, in fact, you would expect ChatGPT to be generating lower perplexity data than the much smaller models used in the other dataset, but in fact, the perplexity classifiers do much better. And we don't have a human baseline for this because that was from experiments from the previous paper. Now, we're going to look at cross-domain validation scores where we fine-tune the models, or we train the models just on 3 out of 4 domains and then test performance out of distribution on the 4th domain. The most striking result here, you can see that the hatched bars are the out-of-distribution performance, and the RoBERTa model in particular is doing significantly worse. Notice particularly the recipes dataset, the RoBERTa score is much, much lower out of distribution. So next we look at the cross-domain validation scores on the RoFT ChatGPT variant of the dataset. And here we're just looking at the perplexity-based classifiers. And we separate out by the different models that are used to generate perplexity scores for each token. And we notice that particularly Phi 1.5 and Phi 2 are doing significantly better out of distribution. On the short stories task and the presidential speeches, their perplexity scores are doing quite well. And this actually makes a lot of sense because these models, Phi 1.5 and Phi 2, they were partially trained on synthetic data generated by ChatGPT 3.5. Next, we look at the cross-domain validation scores when we separate the dataset by the model used to generate the completions. So this is in the original RoFT dataset that used these various small models to generate completions. So we try to see to what extent is the model learning, are the classifiers learning about the particular model, and to what extent do they generalize across other models. And again, we see that our strongest method, RoBERTa, it's doing quite poorly out of distribution. except on the control model. But for GPT-2 and DaVinci, it's got a much lower score. And also, sometimes the topological data analysis is doing significantly worse out of distribution as well. So now we're going to try to analyze features of the text data sets to figure out what is going on, why can we explain any of these results in more detail. So firstly, we just look at the sentence length distributions when we split the original RoFT data set by the model that's used to generate the completions. And we notice that there are significantly different distributions between different models, and also, importantly, the human the human-generated text has a different distribution of sentence lengths. So this is probably a feature that the models are using, that the classifiers are using, and also it explains why the sentence length baseline is actually doing significantly better than random. So next we'll look at the distribution of labels when we split the data set by the model used to generate the completions. And we see, again, there's quite a lot of variability between models, and it's not uniformly distributed. So again, this explains why the modal baseline is outperforming random. And now let's look in particular at the recipes data set, because we noticed before that the RoBERTa model is doing particularly poorly when it tries to generalize to this domain. And when we look at a typical example, we see that the first sentence is extremely long. It's because it's a list of ingredients. So this appears to really be throwing the model off, and it's probably using the sentence lengths as a useful feature in the task, but then this is failing to generalize to this new domain. And this is showing that result again, which is the confusion matrices for RoBERTa. And on the left, we have short stories where it's doing pretty well. And then on the right-hand side, it's predicting mostly 1 as the label. And this is the sentence that just immediately follows the recipe list. And finally, we'll look at the perplexity scores. And the interesting observation here is that if we look at just the human-generated stories, there are sometimes peaks of perplexity where the story changes subject, or there's a plot twist or something like this. And often the classifiers mistake this peak for being the point where the text transitions to machine-generated, because typically we see a reduction in the perplexity when we switch to machine-generated. So this peak, caused sometimes by a human changing topic, gets mistaken for that transition. And that's the end. We hope that this work stimulates more research on this problem.